Good afternoon, everyone. Thank you for coming to listen to my presentation today. My name is Purushoth, and today I'll be presenting um, about using biocarbon as a catalyst support in the Sabatier reaction. So an introduction to the Sabatier reaction, it's an exothermic reaction that converts carbon dioxide and hydrogen into methane and water, and conditions up to 1.5 atmospheres and temperatures up to 450 degrees Celsius. This reaction typically occurs under a metal catalyst such as nickel, ruthenium, or rhodium, and the application of this reaction extends to space habitats to regenerate water for the use of oxygen generations in those habitats. Typically, this metal catalyst would require a support to ensure that the active metal is anchored in the system and facilitates the interaction between the metal atoms and the gas molecules. Typically, in the past, these supports have been used were alumina or silica-based structures, and these are more of metal and ionic complexes. And this project aims to look into the potential of using biocarbon as the catalyst bed for this reaction, mainly because biocarbon, to introduce, it's the solid product from the pyrolysis of biomass at temperatures up to 1000 degrees Celsius and an oxygen-free environment. So in photo here you see that it's a pretty much a solid structure, and with pretty much it appears to be uniform. However, within the structure itself, there are many pores varying from sizes of 0.7 to 2 nanometers, and this allows for the active metals to anchor on inside these pores and help facilitate the reaction much better. Compared to current current supports such as alumina or silica-based ones, biocarbon is derived from biomass, and the associated energy costs are generally just to heat it up to 1000 degrees Celsius, making it potentially much more lower in production costs for this catalyst. As well, biocarbon also contains a number of surface functional groups within it, and these functional groups can also be modified through the various pyrolysis temperatures. So in order to carry out the testing of these catalysts that were been biochar samples coated with nickel, the reactor is heated up until 300 degrees Celsius under nitrogen gas, and once the reaction temperature is reached, the nitrogen flow is discontinued, and hydrogen and carbon dioxide are introduced into the system at a ratio of 4.4 to 1, and the reaction is set to held for 6 hours per each cycle, and the water produced is collected in a vessel, and the gases that are produced are scrubbed and vented. The objective of this catalyst is to improve conversion of carbon dioxide above 85% and the selectivity of methane above 95%, which are goals that are above the current performances of alumina-based catalysts that are been previously worked on by different research groups in the past. The significance of reaching these levels allow for efficient production of oxygen on space habitats and reducing the need to provide new resources such as water for oxygen generation. In addition, this reaction can also be used towards producing fuels from carbon dioxide, which has potential for the future as well. So in a recent test with the catalyst system, under 1.36 atmospheres and 300 degrees Celsius, nickel-coated biochar showed overall increased performance with subsequent cycles of 6 hours, and the positive trend of this catalyst shows promising capabilities of biochar itself. And upon the fourth trial, there is also an instance of an 85% conversion, which is close to the goals that are of this catalyst. However, more work will be needed to determine the long-term effectiveness of biocarbon as a catalyst. However, there are signs to show its effectiveness in the long run. And further work will be done on modifying the pyrolysis temperatures, which will impact the overall structure of the biocarbon produced. In addition, with nitrogen doping, which is a method to increase the absorption of carbon dioxide and help facilitate the interaction between the nickel metal, as well as the gas molecules as well. And finally, the last modification that we consider is the ideal weight percent of nickel in the system, such that the reaction can occur effectively without mass transfer limitations. And I'd just like to take the time to thank everyone for listening to my presentation, and to Professors Jia and Professor Kerr for their support and guidance on this project. Thank you.
Thank you for your presentation. Judges, please feel free to ask questions.
Hi, I can start. So yeah, thank you for the presentation. I was just wondering, can you explain a bit more how this catalyst bed, how this bed is able to interact with the catalyst, or what kind of function groups are there that interacts with the nickel?
So biocarbon can help facilitate CO2 absorption on inside its pores. Basically, since if carbon dioxide is allowed to be absorbed onto it, it's easier for it to interact with the nickel metals on it, which helps make the reaction move faster. As nickel, the nickel catalysts themselves are can easily absorb hydrogen more compared to carbon dioxide, which makes that more effective in that area.
I see. And okay, and why have you set these, or how did you come from the 85%? I think it's the and your objective. Why is 85% important?
85% was just a goal that was above the conversions that I found for previous models of catalyst systems for this reaction. Typically, in literature, I've seen conversions of to around like 70-75%, and so 85% was just a goal to reach through using this catalyst.
Okay, thank you.